Good afternoon, everyone. Welcome to today's webinar with Applied Software, 3 time-saving tips for creating sheet metal parts in Inventor. We're glad you're here with us. This Hangout, as we call it, is brought to you by Applied Software, the premier software systems integrator in North America. I am Jeff Pearson, an account advisor with our manufacturing technology group, and I am delighted to be your moderator today. Throughout the presentation, we encourage you to please interact with us by typing questions and comments using the questions pane. We'll be answering questions at the end of the presentation. This webinar is also being recorded and will be available to you online on our YouTube channel, and we'll send you an email following the webinar with a link to the recording. If you haven't already, search Applied Software on Facebook and like our page so you'll receive the latest information and special offers. And when you visit our website, asti.com, that's ASTI.com, there's a complete schedule of upcoming events, webinars, training, and more. To give you an idea of a few of our upcoming webinars for the manufacturing side, in addition to today's webinar, on Tuesday, March 8th, we'll be presenting new functionality in Plant 3D 2016 Extension 1. Then on March 24th, we'll have a manufacturing hangout, and the spotlight will be on Inventor sketching tips. Then on Tuesday, April 5th, we'll be hosting a webinar entitled Categorizing Your Files with Vault. Very, very good webinar on data management tips and tricks. Also, ask that you stick around to the end of today's webinar. We'll be giving away a $25 Visa gift card, and the catch is you have to stick around till the end to win. So stick around till the very end. We'll draw at random from today's attendees for a $25 Visa gift card. Joining us today as our presenter is my esteemed colleague, Scott Hallmark, one of the premier technical minds in the country for all things Autodesk. It's always a pleasure to be part of these with Scott, and I'm sure that we'll all come away with a good bit of valuable information today. So without further ado, I will turn it over to you, Scott.
All right. Thank you, Jeff. I do appreciate those kind words. Yeah, so today we are going to be looking at 3 time-saving tips for creating sheet metal parts in Inventor. I'm going to briefly cover just the 3 items that we're going to be looking at. I won't keep coming back to the slideshows for this. I just want to cover them real quickly, and then we'll get right into the software and get into what these 3 topics or these 3 tips are going to be able to do for you. First of all, we're going to look at adaptive sheet metal sides to a solid skeletal part in an assembly. So in other words, if you're needing to generate some type of sheet metal structure that's going to be some type of container, a bin, or a hopper, I want to show you how to do this without doing this more as a top-down approach rather than a bottom-up approach of designing the sheet metal sides for this hopper. Instead of doing that one at a time, putting it together into an assembly and hoping it fits, what we'll do is be able to use a solid skeletal part in order to create those sheet metal parts. And by doing that, you're allowing adaptivity to take place, which means, which actually gets us into the next item, which means we'll be able to apply some iLogic rules, some code, and some forms in there in order to drive the sheet metal parameters by that skeletal part. So you'll see how we can, create a hopper of just about any size that we want, based on those driving adaptive parameters in the skeletal part back to the assembly. And then we'll finish up with a new tool that I don't know if you've had a chance to play around with yet, but it is called the shape generator. And it's what it allows you to do is to take those bulky, heavy sheet metal parts and basically run it through an analysis on the front end of the design rather than on the back end of the design in order to cut out some of that excess material, save money on material cost, shipping weight, things like that that tend to make parts and assemblies a little heavy. So we'll look at those three items, and then as Jeff mentioned, we'll come back and finish it up at the end with some questions and the giveaway. So what I'll do is just jump right in here into Inventor. And so what we're looking at, as I mentioned, we're going to look first at adaptive sheet metal sides to a solid skeletal part in an assembly. So you can see I've got something started here, and I created these using this technique. Now, this technique is not new by any stretch, but it is something that I don't know that a lot of people really think about, being able to use the adaptivity in order to create sheet metal parts. So what I've got here is, again, I've got this one skeletal part here. It's called a hopper skeleton. And if I just open that on its own, I've already got it open down here. You can see it's basically just a solid that I've gone in and set up to a clear green so that, when I bring it into my assembly, I can see through it. I can see my sheet metal parts on the other side and make sure everything is fitting correctly and being designed correctly. But if we take this end apart, just drag it up, you can see how easily this has been generated. I create just an initial sketch, extrude it up to a certain height, and of course all those dimensions you're seeing there are named parameters. So I'm defining these names by section 1 width, depth, and height, section 2 width, depth, and height, and then section 3 height. So you'll see as I'm starting to build this by dragging this end apart down that I'm defining the overall height of the hopper, and then going in and creating solids. So I'm creating a loft here, going from one shape to a new shape, which would be this sketch here at the top. And again, those dimensions you're seeing there, they're named parameters. And the reason I want to name these up front is so that I can use them later on in my iLogic code. So that's very important as well. We don't just, in doing this technique, we don't just throw out dimensions and use the default naming scheme, which is D0, D1, D2, but we actually name them something descriptive. So when we go into our code, into our iLogic code, it's going to be very, very easy to map those parameters together. And then we'll take this last end apart, drag it down, and you can see I'm basically taking the outside shape of that loft, not dimensioning it, just doing a project geometry and then giving it a height. And of course, if we look at that extrusion, you'll see that that extrusion is also set to a parameter, so section 3 underscore height. And if you weren't aware, you can name parameters inside of here just as easily as you can name them inside of a dimension line, just by putting your cursor in front of the value, typing in the name, and then making sure you put an equal in between the name and the actual value. So that's really the hopper. That is basically the inside cavity that I want for this hopper or bin. And so what I'll do now is go back to the assembly, and then I can take this. So what I've done is I've placed that in as my first object in the assembly. I've grounded it so it stays intact in place on the origin as I created it. And then I've gone in and I've made a couple of parts already. I'm going to come over and make the other two parts just so you can see the process that we go through to do this. But real quick, notice that it does show adaptivity on those two parts, meaning if the skeleton was to change, then my two skeletal or my two sheet metal parts are going to change with it. So first, let's just kind of go through the process that I go through in order to create the sheet metal part. So I do this in a new sheet metal part template on its own. I do this within the assembly. So I go up here to create, and I'm going to select a sheet metal part to create, And I've already got a sheet metal front and a sheet metal left. This is my front based on what we're looking at up here in the view cube. So that's my front sheet. That's my left. I'm going to create one for the right. So I'm going to use that same naming scheme there. I'll call it SM right. And it's going to use a sheet metal template. But again, I'm doing this within the assembly. And so when I go to pick the location that I want to place the sheet metal part on, I don't want to select any of the existing faces here. What I want to do is select one of the default work planes, in particular the YZ plane that's basically in that same, that same facing direction. It's vertical, which is my sheet metal part's going to be vertical as well, but with some bends in it, but the majority of that part is vertical. So I'm just going to pick this. You really could pick anything you wanted. It doesn't matter. I recommend not selecting the existing faces. Just use existing work planes because they never change. They're default work planes, and they never get moved. So I'll select that to start with, and then all we need to do is start creating sketches, projecting geometry, and then creating a face. And it's just those 3 steps over and over until you have selected all 3 sides of the sheet metal part. So we'll start a sketch on this face. Again, I don't have to draw anything. I just project what is already there. That creates the adaptivity. So there you're seeing the adaptivity sign or the symbol that shows up. So I just have to project it, finish the sketch, and create my face. Now, this is assuming we've got our sheet metal styles already set to whatever thickness or material that we want to use here. So I just select that profile that I projected, select OK, and there's the first face. I'm not going to get out of this yet because I'm still creating sides to this sheet metal part. I've got this angled side here, so you can see it's going to actually bend and come up at an angle and then bend straight vertical again. So the next one, again, same thing. I'll create a 2D sketch. I'll pick this this bent face here, this face at an angle. I'll project that geometry as well. Finish the sketch, create the face. It automatically finds the closed loop, so I don't have to necessarily pick it. Hit OK, and now if you look down here, you can see it's got our bend already in it. And so we're ready to finish it up with the third face here. So again, 3 steps. Create a sketch. We pick the face. Step 2 is project the geometry. Step 3 is create a face. It finds the closed loop. We hit OK, and then there is the bend on that one as well. So if we want to look at this from the side, you can see there's our material. There's our sheet metal part. And now if I wanted to just take a look at this as it is on its own, I can select this create flat pattern, and we can take a look at that part in its flat state. All right, we'll go back to a folded model and get back into the assembly. So let's come back down here let's close this out. We'll save it, and we're back in the assembly. So now, just like the other components here, we have some flanges on top and bottom. So again, I'm just going to go back into that sheet metal part, and we're going to create our flanges using just standard sheet metal tools here. So we'll create our flange. Now, again, I mentioned you can create named parameters right here in these dialog boxes. You don't have to put in a number and then go up to your parameters dialog box in order to name those. We can just call this flange length and then put an equal sign, as I mentioned before, and then whatever it needs to be equal to. I happen to know that these, actually I think these are 4, but if they're not, we're going to let our iLogic code drive these automatically. So I'm just going to put in a flange length equals 4, and then I'll do the same thing down here at the bottom. I'm going to select this bottom edge. Again, it's going to use that, but this time all I have to do is make it equal to that named parameter I've already created, flange length. So I'm not putting in flange length 2 unless they needed to be, if they could potentially be 2 different lengths, then I would want 2 different parameters. But I do want these to be the same all the time, so I'll just make it set it to that named parameter. So now I've got this created, and I'll go to return. And so now what I need to do is do this last one over here. we'll do the same process, just to make sure you get what we're doing here. Oh, and you'll see some planes that show up. All we have to do to clear those is to go in here to into the sheet metal part, turn the visibility off, and come back to the top level, and then we're all cleared up on that. So you don't have all those extra planes sitting out on the screen. So last thing, we'll do the same thing here. SM back, and then we'll make it a sheet metal part or template. Hit OK. Again, I'm going to find that plane that's going through the middle of the hopper. Default work plane, vertical. That's my XY this time. And so now we'll create our 2D sketch on this back side face here. We'll start at the bottom just like we did before. Project geometry, pick the face, finish the sketch, create the face. Apply. Next step, I'll run through these a little bit quicker just so you can see. It tends to go slow when I talk through it. So we'll finish the sketch, face. You can see how quickly you can generate a pretty complex looking sheet metal part that's going to be adaptive to this skeletal part. We'll project that geometry and create the last face. We'll add our flanges here, and I'll go ahead and select that, and we'll name this flange length equals 4. This one I did do a little differently. I made them both on the same selection, as which is different from this. I placed one and then created a second flange, making it equal to that parameter name. This time I just made 2 different selections. All right, so now, actually let me go back in, turn those planes off so we can clean this up a little bit. Turn the visibility off. So now I've got my hopper completed. You can see right down through here we have a good weld seam here that we can create our weld to put this together all the way down to the bottom of the hopper. And what is in green, that is the cavity, that is the volume of this hopper. And so when we define or design that hopper skeleton, we want to approach that as not the outside of the hopper, but more of the volume of it. All right. So now let's take this, and so we're going to start looking at the other option, which is using iLogic in order to drive sheet metal parameters. And we're going to apply some parameters that are going to drive this shape, but it's also going to be driven from the assembly. I don't have to go back to the skeleton in order to change the shape of this hopper. I'm going to do it right from here. So what we do is we go into iLogic. If you've never used iLogic before, you'll find that under the Manage tab. You come up here to iLogic Browser, and that opens up this dialog box here. You can dock this on left, right, or just kind of have it floating out in space, or off on another screen if that's what you want. But I've already created one rule here. I'll kind of briefly explain what we're seeing. I put a couple of notes in here, some comments to kind of let someone know that was going to use this model, what I'm doing here inside of the rules. But basically what I'm telling it is I've got parameters that are named in my assembly, and if I was to change any of those parameter names, I want them to push back to the skeleton file. So if I change the discharge width of in my assembly, I want it to go back and change the skeleton section 1 width. Some people make these the same name, which obviously clarifies things, but I did this on purpose to show that you don't have to make them the same name. You can have discharge width value is going to push back to a section 1 width parameter in the skeleton. But down here you can see that I did use the same parameter name, so the flange length in the assembly is going to push back to the flange length of the sheet metal parts that I create. So there's one in here I don't need, so I'm going to create 2 new lines here showing how easy it is to create this code. You don't have to remember too much syntax here. If you can double click, you can do a lot inside of iLogic. So what I want to do is, again, push that flange length that I set in the assembly and push it back to the two new parts that I created, the right and the back. So what we'll do is we'll come down here to the model parameters, and if you scroll down, you'll see you'll eventually come to one that we created, that flange length. So I want that right here. I'm going to put my cursor here and then double click on flange length. So it pulls in that sheet metal right, flange length, and then all I have to do is tell it what it's equal to. And it's going to be equal to a parameter that I created in the assembly, which is going to be a user parameter, and it will have the same name. So there's flange length there. Simply double click it. That code is ready to run. Okay. I'll make another line here. This will be, instead of the right, we're going to go to the back, and we'll pick the model parameter, flange length. Double click it, make it equal to, and then we'll take that same code that we used up here, the user parameter. Now you can always come down here, find user parameter, double click, or you can just double click inside of your existing code if you know it's going to use something that's already there, and do a Control-C, Control-V to paste it, and it copies the exact same code. So we're basically finished with this at this point. There's some other things that are going on here, like defining the overall shape of the hopper. The section 1 is dealing with discharge, section 2 is dealing with your inlet, and section 3 is dealing with the height of the inlet. And then you've got some holes, and I'll show you how we generate some code inside of the pattern tool in order to or not code, but an equation, in order to equally space holes out, leaving a certain distance on each end, based on whatever we do with the hopper as far as the size is concerned. So we'll select OK on that. That's going to allow us to keep that code. If we did anything wrong in the syntax, it'll bring up a message telling you what line that syntax error was on. So don't get too scared of iLogic if you haven't messed with it before. It's a fairly simple tool to use. So that's the code. That's the rule that we've generated. Here you've got forms, and so what I've already done is created a form, and I've gone to the extent of adding some additional functionality into this form. So you can see here we have the total height of the hopper. I'm going to make a few changes so you can see what's actually happening here. So if I change this from 48 to 42 and then tab down, you'll see that this hopper automatically moves down in shape. Not only does the skeleton update, but all the sheet metal parts as well. So I can take this and I can make this a template. If I'm generating a lot of hoppers for assemblies or any other type of component that you can use this functionality with, you can save that out as a template, and that way you bring up a sizer like this or a iLogic form, modify a few dimensions, and everything is automatically updated into that new assembly, which you could then link in drawings and have drawings automatically updated as well. Especially if you're using Vault and using some copy design, that works great. Flange length, I mentioned that before. These are all set to 4 inches, but if I decide I want to make these 3-inch flanges, you can see how they all automatically update because of the rule that's pushing that value to each one of my sheet metal parts. So go from a 3 to a 6. They all increase in size. I'm back down to a 3. Down here, you've got some other things that we've defined in here in this rule, like your inlet size, your discharge size down at the bottom, and then the holes themselves. I've got 5 holes across here, but you'll see as I go in and I make changes to, say, the inlet or discharge, I may want to adjust these holes. I only did holes here. I didn't do them everywhere else, just so I can show you the functionality that is in here that you can utilize inside of not only iLogic, but creating equations in order to drive geometry like this. So as far as the inlet, that's this opening at the top for this hopper. Say we want to increase this height right here, this vertical height. I need that to be 12 instead of 6. I'll just type that in. You'll see it automatically update. So now that's a 12-inch height. Notice it didn't add any height to the hopper because That's handled here in the total height. Total height from top to bottom is 42 inches, and that won't change. But what will change is the different dimensions values that we put in between. Let's say the width of this needs to be 48, and so you'll see that modification take place. And then also I'll make this 48 as well, so it's square at the top. Now for my discharge though, I don't need this to be square, I need it to be a rectangle. So again, we have that same option to go in, and we can say, you know, this doesn't need to be 6, it needs to be 4 inches instead. So it's going to shorten this up a little bit, add a little bit more length here to the slanted or the angled part of my sheet metal. And then I can go in and tell this needs to be a certain width and certain depth as well for the discharge. Maybe it has to fit on another piece of machinery that's, you know, 12 by 24. Well, I'll just put in 24 for the opening on the width, let that update, and then 12 for the other side, and then click away, and we'll see that one update in this direction. So you can see how easily we can create this hopper and have it change not only the skeleton, but also the sheet metal parts as well. Now if we come over here to the holes tab, again, iLogic is being utilized, not only iLogic, but equations. So I'm going to, before I make any changes here, I'm going to show you the equation that was created inside of the parameters dialog box. All right, so you have your assembly here. This is the assembly parameters. This is not where the equation takes place. The equation is actually in the part itself. So I just need to go to that front sheet metal part, and then if I look at my parameters here, we'll see as we scroll down that you'll see here, right here, that we've got some an equation defined. So let me zoom in a little bit so you can see that. I'm using some named parameters already, like the sheet metal front inlet holes length divided by the inlet hole quantity minus 1. And that will give me equal spacing based on the number of holes. So the hole quantity is driving the number of holes minus 1, and then divided by the length of the holes minus the space on the ends. So and so that a value is here. So we had a 45 length is actually 48, and I took 1.5 inches off each end, which makes it 45. I know I'm getting a little deep in the weeds here with that, but just to let you know, you can generate equations like this that will kind of take some of the pain out of placing holes on parts, and if things were to change, having to go back in and modify those hole patterns and things like that you may have put just static numbers in. If you use equations like this, it's going to speed up the process pretty drastically. So I don't want to make my whole number or quantity change in this. I want to make that in the assembly, and I have that added as part of my form. So on the holes tab, I can say, you know, we've got 5 holes here. This really needs to be 8. So I'll just type in 8, hit enter. You can see they're still equally spaced. They're still 1.5 inches off the ends. But now, you know, the hole diameter, that may need to change also. I don't need a 1-inch hole. I need a 1/2 inch hole. So by linking that back into the part through iLogic, I'm allowing one location, level of the assembly, to drive holes, the size of the sheet metal, and the bend radiuses, everything, or the bend angle, and all that is defined by the assembly itself. So hopefully that helps you out with being able to generate some components using a skeleton solid to do that. So we can take questions on this at the end. If you have any, you can go ahead and be sending those in to Jeff, and we can address those at the end of the webinar. But right now I'm going to jump over to the third item, which was using shape generator on a bulky or heavy sheet metal part in order to lighten it up some. So this is a sheet metal part that I've created, and you can see I've got you know, 2 flanges on it. You've got those over here. We've got flanges on it. We've got some holes created on those flanges so that it can be mounted to something else. But then I've also got a hole in the middle that's going to be, something's going to be, it's going to pivot around that. And so I want this, I need to be able to remove some material from this. So let me get this over here set. And so what we're going to do with this, the way the shape generator works is that it utilizes the stress analysis environment by moving it up front in the process, in the design process, and it balances out the metrics such as factor of safety, and in this case, in mass, I want to remove some of this material. I want to make this lighter. I want to lighten up this overall assembly that I'm creating. To optimize the design and to essentially leave you with the minimal amount of material you need to meet your design criteria. So I know my areas that have to be fixed. My bolt holes here, those have to be fixed areas. I know my area here is something that's going to be inserted into this and pivot around it. So I know this needs to maintain its shape. But also this around here, I know this distance here, I really need to maintain this thickness around this part. So I'm going to use a couple of tools inside this shape generator in order to define those parameters. And then I'll let it spit out or give me a result of how much of this material do I actually need. So what we'll start with is first, just so you see the size of this, I'm going to go over to my physical tab, and this material is set to generic. I want to change this to a, we'll change this to a steel alloy. And so now you can see the weight of this is 8.48 pounds. I need to get this somewhere around 4.2, something like that. About 50% is what I need to take out of this, but still maintain that design criteria that I need to so that it doesn't buckle, it doesn't break under the loads that I'm going to put on it. So we find this under the 3D model tab. It's called Shape Generator. This is new. So if you haven't used it before, you're going to get a real quick demonstration of how to use it. So when I click on Generator, it takes me to a new window here, an Analysis tab. And so there are some things that I can do. Just by clicking on Shape Generator, it created a new study for me. So I'm in this Shape Generator, and there's a few things that I need to define. So here it's already set to steel alloy, which is what I just set it to. But I need to go in and assign some constraints. If the material was not set, I would do that here under this Assign Material. But I want to fix a couple of constraints, and that would be where it's going to be bolted to other parts in the assembly. So I'm going to go ahead and fix those bolt holes. I'm just selecting the edge of those. Very simple to do. And again, I've got a pin or something that's going to pivot around this, so I'm going to select the inside face of that opening or that hole there. Now I need to start applying some forces. I know that I'm going to have something bearing down on this end, some weight on this, and so I'm going to define this as 120 pounds on this end here of force, and on this back end I'm going to do we're going to have 200 pounds of force on this end over here. So I'm just going to apply those numbers in there. But also mention that I need to maintain this thickness around here. This was already kind of predefined. It allows for a clearance for something else in the assembly that this is going to fit around. So I want to preserve this region here. So what I'll do is I'll go and go ahead and preserve that. And so all I need to do is pick this fillet, this curved face on the outside, and you can see how it's going to preserve that area. So as it goes in and it tries to generate a new model or a new mesh for me to remove material, this is going to be maintained. Okay, and then the last thing I want to do is look at the shape generator settings. Remember I mentioned that I need about 50% of this removed. Right now it's defaulting to 60%. I don't need that much removed. I really just need 50% of this removed. I need to get this down around 4.2 or 4.3 pounds. So by changing this to 50, my mass target now is going to be 4.24, and it's going to do its best analysis in order to get me to that with and still maintain the forces on my flanges and maintaining this as a preserved region. So once I've got that complete, I'm ready to generate. So I'm going to go generate the shape. Tell it to run. And so this is going to kind of run in the background, or really in the foreground. There's not much else I can do. I can zoom in and look at things, but this is going to be running and doing a quick analysis on this, again, on the front end of the design. Not having to finish this up and then take it out to an analysis tool. I'm doing this while I'm in the part itself. So here you can see, based on the criteria I gave it, it got it down to 4.2 pounds. It's a mass reduction of 50%. And so really all I need to do at this point is go in and make a couple of sketches here in order to cut out material that is not needed for this part. By having what we're seeing here, this is going to maintain this structurally sound and meet the design criteria. So if this is good and this is what I want to end up with, which it is, I'm going to promote this shape up to the part. So I'm going to select this and send this up to the current part. I could create an STL file of this if I wanted to, but I'm just going to promote this up to the current part file, which means over here in the browser, we now have that showing up as part of our sheet metal part. So now I just need to define some sketches and cut away material, and we simply do this by sketching and cutting. So I'm going to take a few minutes here, and I'm going to project some geometry, which would be the outside face of this. I need that, and then I'm going to define some areas to cut. So I'm not going to necessarily go into the yellow. I could and still take this back out to another analysis tool and make sure that it's giving me everything I need. So you can see I'm going to cut through the yellow a little bit right there. That's okay. It's still going to be structurally sound. So let's finish this off with a part over here, line over here. And so what I'll do at this point, I could go ahead and sketch everything else if I wanted to, or I can just finish this sketch and go ahead and cut. I'm going to go ahead and finish the sketch, but before I do my cutting, I'm going to share this so I can come back to this sketch and do this. Let me cut it first, and then we'll share the sketch. So I'm going to hover over this. We'll do a select other, and we'll pick that profile body to remove. And so that's removing that part. This is not needed anymore, right? So I'm going to go back to my sketch. We'll share it. And so now I can just go back into that same sketch and continue generating my cut. So I'm going to use this existing geometry here. I know this is going to be maintained, so I'm going to just draw a couple of lines off of this circle up to this corner, over here and back down to the circle. And so I know this part can come out as well. Let me just go ahead and do a quick arc here. Sometimes the lines don't necessarily show up as a closed loop, so I'm going to modify it so that it does. And so I'm going to come out here, come straight down, straight across. I'm going to try to get that parallel, and there it is there, constraint, and then back up here to the existing line. And I'll draw a line connecting those again, just so I know that I have a closed loop. And then we'll do the last one down here. This time I'm going to come off of that circle, come up and over and down. So all this material that I'm removing, again, it's not needed. It's not needed for the part. It's still going to be structurally sound. Let me take that one off. Did not pick that one correctly. Let's come down to here. Okay, and then we'll finish this line up, coming over here to this tangent line, and then I'll put in another arc between here and here. All right, we'll finish the sketch, and so now I'll go in and again do my cuts. I'm going to hover over, take that body out, that one, and that one. So when we select OK, those are now cut from the material, and so I'm ready now to turn off my sketch, turn the visibility off, and we'll turn the visibility of the shape generator off. And so now this is a structurally sound part that is half the weight, basically. You know, we could always come in here and add fillets for corner rounds in order to clean this up a little bit more. It's certainly up to you how you want to do that, but again, very simple to do, just to go in and add those corner rounds in and clean this up some. Now I could have gone through and done a lot more with this to make it look better, but now that this is created, let's go and take a look at the properties of it now. We'll go to iProperties, go to the Physical tab, and we'll do an update. So now this is 4.8. Still did leave a little bit more material in there than I wanted to. So I could still go in, pull that, or turn that shape back on, and then further define how much I want to remove. But this is structurally sound, and in order to, you know, to test that, let's just go back into that, into our analysis. So I'm going to go over here to stress analysis, and I'm going to create a new study. All right, and so again, I'm going to, this is using just the analysis tool. This is not a shape generator. This is just using the analysis tool that's a part of Inventor Professional. So again, I'm going to apply my forces here, just like I did before, 120 pounds on that end, and then we have 200 on that end. And I'll set my my fixed locations here with the holes where the bolts would go through, and also a pin location here. Basically the same same items I was telling it to do before. But now we'll run this through a simulate and let it do an analysis on this part. Now this is showing a lot of exaggeration on this, but let's actually show an actual deflection. So you can see that based on this, on my loads, my forces, everything that I've applied here, that this shape is going to hold up without question at all locations. Okay, you know, you can go with your simulation. You can go and set up safety factors and different things like that. But this is going to give me exactly what I need, and it's a much lighter weight part than what I was dealing with before. So we can finish our analysis, and we are completed with the part. So Jeff, I'm going to kind of call you back in here. Let you can ask any questions that have been submitted to us for this demonstration.
All right, good deal. Thanks, Scott. That was some really interesting stuff. I hope those of you in the audience were able to pick out some things that you can use and take back to your job and make it a little bit easier and a little bit faster. So at this point, yeah, if there are any questions, anything that you'd like some clarification on, don't have anything in the questions pane as yet, but would like to hear some feedback from some of you, whether question, feedback, anything of that nature. How can we add to what we've provided for you today? We've got a shy crowd today, Scott. There we go. Okay. Manoj, thank you. This is very nice and informative. We appreciate that. We always strive to bring additional value to our clients, so thank you for that feedback. Tom Drawdy would like to know where he can get more info on iLogic.
Okay. Well, actually, we do teach a class on iLogic. You can find several things online that are available, some white papers and things like that. Probably some AU classes if you go look at the Autodesk University. but we do provide a class as well. And what we would do, we can do just a general, this is iLogic class, or we can get custom with you and kind of look at your parts and help you generate some iLogic code to help drive those rules, rules-based engineering into your parts and assemblies. That's really the most beneficial is the latter of the two that I just mentioned, because that really gets you on the ground and running with using iLogic and being able to utilize it immediately with common components, common parts that are similar in shape, but that just change size. You just need to add some, make it longer, make the whole quantity different, whole size is different, and be able to handle everything from an assembly environment. That's just a portion of what iLogic will do for you. It's a pretty extensive little. I don't want to say an add-on because it's not. It's part of Inventor, but it's something that most Inventor users really don't even realize it's there. But yes, applied software can certainly help you out in that area with custom training or just a generalized this is iLogic type training.
Yeah, and Tom, you can always reach out to one of your account advisor team for additional info and that sort of thing. So don't hesitate to reach out to your advisor with specific questions or needs there. The good news, Scott, they've gotten over their shyness. We got a few more questions here, so okay, this is great. We woke them up. Right. Lottie Allsbach has a question. Is all of the functionality for what we were just shown inherent to the default install of Inventor?
Well, that depends. Well, I don't know if it's part of standard or not. I know it's a part of professional because that's what I'm using. So I know it's a part of Inventor Professional. I'm not positive if it's part of standard because you also get that analysis in the professional version, simulation or analysis tool that's built in. So without knowing for certain, I would say that it's part of professional only. But what I can do is I can clarify that and make sure it was part of the R2 update. So if you haven't loaded the R2 update, there's actually an R3 out now that added some additional stuff that we didn't even talk about. So make sure that with your 2016 Inventor that you are at least up to R2 so that you can see that shape generator.
Okay, thank you, Scott. Next, this question is from Barton Crowell. Is there a reason to join the parameters through iLogic rather than link the parts through the parameters to the skeletal part?
They both work. They both work just fine. The reason I tend to do this through iLogic is if we are going to make any if we're going to use this as a template, okay, so if it has a new file name call out, that file name is updated in the iLogic. The linking, however, may not, if I remember right, it doesn't update automatically. I'd have to test that out to be 100% positive on that, but I like to see all of what's being linked from parameter parameter of the assembly back to the parameter of the part all in one location. I don't want to have to go to all my parts to see that, or go to the assembly parameter dialog to see all those, and hope the file still exists or nothing has been changed inside it. When you change a parameter name inside of a part, it updates in the assembly or in the assembly iLogic code. So that is, it kind of makes it, I don't want to say break proof, but it does help in that, making things continue to work. But it's a preference. I just like using iLogic. It's just to have all those tools right there in front of me and be able to do so much more than what we're talking about here.
Good deal. A couple of folks had the same question. Manoj and my friend Brian Howes both asked, will the entire webinar be available in recorded format? And the answer is yes. You'll each receive an email after the conclusion of the webinar with a link to the recorded version. It will be out on our YouTube channel shortly after the conclusion of today's webinar, so it'll be available to you to review downline. Let's see. Trenton Adams asked, what was the tab named Cool Orange?
That's actually an add-on that I use. If you go out to the App Exchange, there is you can download apps that go, that kind of add functionality into your Inventor. And so let me just swap back over to Inventor for a second. I'm trying to remember what all I had in here. Yeah, this one is a screen grab. So if you don't have something that will do some type of screen capture, it will go in and capture screens. And then there's a feature migrator. And so what this allows you to do is kind of take features that are created in the assembly and push them back down to the part. If you create assembly features, they don't always get pushed back to the part, and that can be a problem when you go to detail that part. Well, this kind of pushes that to those parts. So that's what Cool Orange is. It's just a company that writes some add-ins, and that's where I got it from. That's one of the reasons I have it in there.
All right, good deal, thanks. This comes from Tony England. Would the hopper idea work with a round outlet, Scott?
Oh, certainly, absolutely, no problem.
Okay, easy.
And now, if you're talking about a squared around transition, I've never tried that, but I don't see why it wouldn't work. It's a parameter, and it's being driven by a value. So, and when you do a squared around transition, you're doing basically a loft from a round to a rectangular or square, and it's just parameter values. So I don't see why that wouldn't work. It'd be interesting to test that out. In fact, I might test it out when we get done here just to see if that would work. I don't see why it wouldn't, though.
Okay. Scott Sanders wanted to know, I take it that you can set and adjust your thickness.
Yes, of the sheet metal, yes. If you just go ahead and predefine your sheet metal style before you get started in the assembly, and have that style available, so every time you go to create that new sheet metal part in the template, it's already set to a particular style, sheet metal style with a certain thickness defined. Yes, you can do that. You can then also go into the sheet metal part itself after you've created it and modify thicknesses there too.
All right, great.
Manually modify them, or change the style to a different style that has a different thickness, different gauge.
Okay, great. From Randall Brown, can this functionality be used with plastic sheet or cardboard sheet materials?
Again, I don't see why not. This is not just functionality within. Well, let me think about that. If you create a sheet metal part, but then just set the material to that material, you'll still have the bends, the bend radiuses. Yeah, I don't see why that wouldn't work. You would still use a sheet metal template so that when faces meet other faces, they automatically add that bend in there. But I don't. That would just have to be something we'd have to test out. I don't see why it wouldn't work. Just change the material to a plastic, but still use a sheet metal template so it uses those sheet metal properties to define bends and things like that. So we would have to test that out to make absolutely certain.
Okay.
I will say I have not done that with those materials before, so that's why I don't have a 100% confident answer in that question.
Okay. And again, from Tom Drawdy, will the iLogic assembly template save the individual parts as a different name?
You could do that if you were using Vault. You could do that as a copy design. Take the hopper itself and then go through your renaming options through Vault and copy design. But as far as the sheet metal, or I'm sorry, as far as iLogic creating new file names, I won't say that possibility is not there. Again, that's one of those things that I've never tried. If we just we try to use Vault and all the functionality of Vault, and that handles that very well.
Yeah, great questions, guys. Great questions. Let's see. Oh, where do you get Cool Orange again, Scott? Where do you get that?
That is from the app. Let me see where it's at. If you come up here to the white and blue X, that's your Autodesk App Exchange or Exchange apps. If you click that, it's going to open up a web page, and in that web it should take you to it. It's running a little slow right now, probably because I'm broadcasting over GoToMeeting, but it takes you to this, and so there's Cool Orange app right there. You could do a search here for Cool Orange, or under publishers you could type in Cool Orange and see all of their apps. But there's some about several in here. Applied Software has some in here as well. One I know of in particular for Plant 3D that my colleague Dennis wrote. So some of these are in here from Autodesk. A lot of these are in here from individuals and other companies that have written tools that can go along with your application. Some are free, some cost you. So it just depends on if it's a necessity. You may have to pay a little bit. Some of these are a couple of dollars. Some of these are more than a couple of dollars. There's $1.99, $7.99. So it just depends on what you need. They usually are a per seat type installation, not a site license type thing.
Okay. And looks like last question. Does 2016 Pro have an option for colorblind designers? As colors tend to blend together during the stress analysis and draft.
Mm-hmm.
That's
a great question.
Is there an option there? Yeah, that is a great question. I like that. Thank you, Trenton.
Yeah, I really have no idea on that. I know that Inventor allows you to modify color schemes because of that reason, but as far as the output of an analysis, I have not seen an option to change that color scheme to benefit those that are colorblind. So we would have to research that and see if that's available. I have not yet.
Okay, good deal.
I've never been asked either. So
yeah, that's a great question. That's one I had not been presented with before either. So again, great questions, folks. Thanks so much for throwing those out there for the benefit of the group. And we sincerely hope that you were able to take some value out of this today. I'm going to go ahead and throw everyone's name into our random generator here and let it run for a second to select the winner of our $25 Visa gift card. And just if your name comes out, I'll ask that you type into the chat window anything that you like, just to indicate that you are indeed still here live and in person. So let's see, let's run the little wheel. And thinking. And okay, here we go. The winner of the $25 Visa gift card is Brad Trotter from Habersham Metal Products. Brad, are you still with us? Yep, there he is. I see it in the questions pane. He is still there. Good deal. Congrats, Brad. We will be sending that over to you in short order. after the conclusion of the webinar. And we're right on time here, so again, we want to thank all of you for joining us today. Be sure and go out and check on our website for upcoming webinars. We will, of course, be sending further information out as those become available. Thank you for being part of this today, and with that, we will bid you good day.